So our next presenter is one of our guest speakers, and we have Carmela introduce Mr. Khadak.
Hello, everybody. This is my newest roommate, Anoj. We were in the same room last night in the dorms. It was great to meet him. Super excited to have you. So Mr. Khadak comes from Nepal and completed his Master's of Science in Physics from Nepal. Mr. Khadak is a fourth-year graduate student at WPU, completing his PhD in Physics. His research interests include pulsars and algorithm development for pulsar searching. And outside of academia, he loves cooking as well as hiking. And we were talking a lot about this yesterday, which was really cool, that having arrived from a country with lots of mountains, West Virginia naturally feels like a home away at home. So we're super excited to have you. And yeah, thank you so much for being here.
Okay. Hi, everyone. So I thought like amateur is kind of like misnomer because hearing some of the talks, I feel like a lot of people know here much more than I do, and I just recently started. Maybe like I'm good on the science side, so I didn't know like I try to like keep science at like basic level so that it would be easier to understand from people from the all kind of background. But anyway, I try my best. So today I'm going to present about the long period radio transients. So this is a recently discovered phenomenon in radio astronomy. So I guess
And you use an arrow keys to slide in. Maybe the page down.
okay, so I have structured my presentation into three different categories. So first, I'll briefly introduce about the background of the topic I'm going to talk about, and then I'll say some of these long period radio transients we have discovered, and then I do my presentation with the conclusions. So, okay, first, a brief background about the subject I'm going to talk about. So what are radio transients? So pulsars and FRBs are two radio transients that we have been studying in radio astronomy for a while. So pulsars we have been studying for 6 decades now, and FRBs for around 20 years by now. And so what are pulsars? So we have a star. So not all the stars are pulsars. There are like particular kind of star, neutron star basically. And these stars are spinning, and as they spin, they emit the beam of radio emission, and after a certain period of time, we see this radio emission coming from these stars. And these are repeating periodically, and that is what the pulsars are. And the FRBs, we still do not know for sure what are these objects. We predict they are likely to be some kind of neutron star, but still we are not sure like what kind of object they are. But we know for sure like they emit some kind of radio emission, and there are both repeating and non-repeating FRBs. So we have seen one of burst coming from this source, and also we have seen these radio emission like coming from that source periodically. So, but in terms of energy, the fast radio bursts are very high energetic event, whereas the pulsars are less compared to the FRBs. But in terms of the period, like the period in which the radio emission we see coming from them. So for the pulsars, the period is around like few milliseconds to few seconds. And for the FRBs, the period is around like few milliseconds. So these are two of the transient objects, and the reason we call transient is like we are seeing the emission for a very small fraction of time, like few milliseconds to few seconds. And these we have been studying for a while. So these are the known radio transients. But recently we have started to see a long period radio transient. These are discovered like 4 or 5 years for now. And what might possibly be the likely candidate source for this kind of objects? For known radio transients, for instance, like the pulsars and FRBs. For pulsars, we know for sure they are neutron star basically. But for FRBs, we still are not sure what they are, but the most likely candidate is like either magnetar. Magnetar are basically the neutron star, but they are very high magnetic field. That is what we expect it to be. So I'll briefly discuss about what neutron star and what these two are the likely candidates for these objects. But we are not sure, but from based on the scientific analysis, we expect that these are the most likely candidate. So what are neutron stars? So not all the stars live same and die same. So some stars that are in the mass range of 7 to 20 solar mass. So for people who don't know what solar mass is, like the mass of the sun, we use that for measuring mass of stars. So when initially the stars had mass of 7 to 20 solar mass. So at the end of the life, these stars end up being a neutron star. And the reason we call neutron star is they are very, very extremely dense. So at the range of 10 to the 17 kg per meter cube. For perspective, the density of Earth is like 5,000, 5,500 kg per meter cube. But these have density of 10 to the 17 kg per meter cube. And they are mostly consisting of neutrons. So what happens is like at the end of the life, these stars, the gravitationally, all these materials are so tightly squeezed that the only particle that can survive here is neutrons. And neutrons are subatomic particles. So that's the reason we call them neutron star. And they have a very high magnetic field. So the magnetic field is in the order of 10 to the 12 Gauss. For perspective, Earth's magnetic field, Earth also has a magnetic field, and Earth's magnetic field is just 0.5 Gauss. And these are magnetic field in the order of 10 to 12 Gauss. And as I told you, like these stars are like 7 to 20 solar mass, and they are squeezed to the size of 10 to the 12 kilometer, even like smaller than New York City. So this picture is just trying to like show the perspective like how big they are in terms of size, but in terms of mass, they are like much more massive than sun. So that tells us like how extremely dense these objects are. So this is one of the potential candidates that we expect these radio transients to be. And the other one is white dwarf, what we call white dwarf. So white dwarf, these stars, these are also like the end product of the star. So the stars that has less than 7 solar mass and around 1 solar mass, for instance, our sun, at the end of its life, will end up being a white dwarf. And these have density in the order of 10^9 kg per meter cube. These are also extremely dense, but compared with neutron star, they are slightly less dense. And also they have high magnetic field as well. And the difference between the neutron star and the white dwarf is these start from slightly less massive stars than the neutron star. And these are like, as neutron stars are squeezed, these are also squeezed by the gravitational force. But in case of neutron star, what we call neutron degeneracy pressure. So when we squeeze the atom, then the charges will try to like repel that. And for the case of neutron star, the ultimately we cannot compress further than the pressure exerted by the neutrons. But in case of this, the pressure that supports the further collapse from the gravitational field or the gravitational force is the electron degeneracy pressure. So this white dwarf is another potential candidate that we think would be likely the candidate source for the radio transients. So these are the two likely candidates. Okay, and I'll just briefly talk about how these white dwarf and neutron stars form. So there are like huge amount of dust clouds of gases in the space, and they start from the clouds of gas, molecular gas, and if the cloud has enough high mass, the gravitational collapse, and they start with the high mass star, and then in the due course of the evolution, this high mass star will become a red supergiant. So red supergiant is the case like there is a star, and in the due course of evolution, the outer layer of the star is highly inflated and they expand in size. So they become a red supergiant, and in the due course, they burst into an explosion. They explode into a supernova, and if they start with a very high mass star, they end up being a black hole. And these are the stellar mass black hole that was detected by LIGO observatory. But if they have slightly lower mass, they end up becoming a neutron star. So that is how neutron star is formed. And if they end up, if the gas cloud in the space starts with slightly lower mass, then they follow the different evolutionary track. And they become a main sequence star, which our sun is also a main sequence star now. And then in the due course of evolution, the outer layers expand and they become a red giant. And at some point, our sun will also be in the phase of red giant. And by that time, the Earth will also be swallowed by the sun. For instance, there is a track outside. They have kept like where the sun is, where the Mercury, and like it goes all the way up to the telescope, just for the perspective. So imagine like at some point, the sun will be as big as like where the Earth is. So we will be swallowed by the sun when it reaches the phase of red giant. And then all the outer layer will be settled, and the inner core will just be what the white dwarf is. So in that, the outer core is like what the sun will set at the end of its life. And the inner core will just remain as a white dwarf star. And that is how we end up getting a white dwarf. So white dwarf and the neutron star, that is how the evolutionary track of the star will look like. So that is how they form. And these two are the most likely candidates for this radio transit. So now I'll give few of these long period radio transients we have discovered. So these are different from the pulsars and FRBs for the reason that they have very long period. And we have been starting to discover them for like past 2-3 years only now. Okay, so this is Murchison Whitefield Array Telescope in Western Australia. And these are patches of these low band antennae scattered all over the places in the Western Australia. So they use this telescope, they were doing a low frequency survey of the sky, and then they see this signal, radio signal coming from certain location in the sky, and they make a follow-up observations, and each of these signals are repeating after every like 18 minutes. So pulsars, FRBs, they repeat around like few seconds or few milliseconds. These are like reading after like few minutes. So that is very strange and not observed before. So they see this, and this was the first long period radio transient discovered, and so discovered around 2022. It has just been a few years. And they have a period, this max, and that's the coordinate value, and it has a period of 18.18 minutes, and it is at a distance of 1.3 parsec, which is 1 parsec is around 3.2 light years. And this is the first long period radio transient discovered. So until this point, we have only discovered like 6 or 7. I haven't checked like the past few weeks because discoveries are happening very like rapidly. There might have already been added like few of these, but from the last time I checked, there are only like 6 or 7 long period radio transient discovered so far. So I've just picked a few of these. And this is the first one they discovered in 2022. And so there is another one that was discovered by time. And we also have a time outrigger here outside. So the other one discovered by the time telescope in Canada. And this other long period radio transient that was discovered using time telescope. So this is the one that has the shortest period, and this is the one that was discovered, and this is the nearest LPRT discovered. So this image is just an X-ray image. So they see something and they try to see from other telescopes. And this is the X-ray image. And the white circle there is just the localization of where they see this signal coming from. But this long period radio transient discovered has just a period of 421 seconds. And this is the nearest one we have discovered so far. This is only at a distance of 170 parsec. So this is another one with the shortest period and the nearest one we have discovered, and that was discovered by time. So I'll give you another example. So this one is SCAP telescope, that is Australian Square Kilometre Array Pathfinder, that is in Western Australia, and this is the precursor of SKA, which is Square Kilometer Array Telescope, which is one of the next big thing in radio astronomy. So using this telescope, they discover another long period radio transient, and these are the light signal coming from, and this has a period of 6.5 hours and located at a distance of 3.7 kiloparsec. So I just picked these three examples just to give you like impression of like how wide range in the period they are. So this one with the shortest period has a period of 421 seconds, and to date, this is the one that has the longest period, which is 6.45 hours. That is like huge range in the period. So that is also like very interesting thing about this thing. So, but for instance, like in case of like pulsars and FRBs, it's not like very like wide range in terms of period. But these have like very wide range of period, and there is no any like scientific guarantee that at some point we might start to see long period radio transient that has a period of like 1 day or 2 days. That would be interesting. So these are just like three of the examples that I picked. And also we have like all different kind of telescopes like observing these things, and especially observing at like low frequencies. So now the natural question is, these are most likely in terms of physical characteristics similar to pulsars and FRB. So this is a popular diagram in pulsar astronomy. I'll briefly explain. So on the y-axis, there is a period derivative. What period derivative is? So as all the stars are spinning, and for instance, neutron star is spinning, and you see this radio emission coming from the neutron star, and as they keep on spinning, they lose energy, and in the due course of their life, when they lose energy, the rate at which they spin will slow down because they lose the energy, they don't have more energy, so they start to spin slowly and slowly and slowly. So that y-axis is telling like at what rate the spin is decreasing. And the x-axis here is the period, just at what frequency is reduced. So we use this diagram to classify these objects, and these are the pulsars, and the crossed brown objects are what we call magnetars. Magnetars are basically neutron star, but they have very, very high magnetic field compared to the regular neutron star. And those are the long period radio transients. So if we see in this diagram the location of these objects, what this is telling is in this diagram, so as we move further on that side, the magnetic field is increasing, which means the one on that side, they have higher magnetic field. So the magnetars, they have high magnetic field, and these are regular pulsar, which is regular neutron star, slightly less magnetic field. And the long period radio transients we have discovered lie in that region. So what's the difference? They have very long period, and in terms of the physical characteristics, they're similar to magnetars or neutron stars. And so this tells us that they are most likely either neutron star and white dwarf in some kind of binary system law. And the arrow that we see there, those are just the upper limit of the magnetic field of these objects, but it could have magnetic field as low as pointed by this arrow. So which tells that it could be similar to either a pulsar or like magnetars. So most likely candidate would be like neutron star or white dwarf. So that is what this diagram is explaining us about. But the other problem we have here is these two lines are what we call death lines. So what death lines is there? So as the neutron star like keep on spinning, they lose the energy, and in the due course of their life, we don't see any more radio emission coming from them because they have lost enough energy. And below those lines, we don't see radio emission. So that's why we call them death line. And these two lines are different, and depending on what kind of magnetic field these neutron star have, that will determine whether they will keep on emitting radio emission or will stop. So if a neutron star has a regular dipole, which is like the magnetic field line, if they have a regular dipole, The dotted line is what is the deadline for those kind of neutron stars. And below that, we don't see radio emission. But some neutron star could have a very twisted magnetic field line. So if it is in such kind of twisted dipole, so that would be the deadline for those. And those kind of neutron stars will still be able to emit the radio emission, and we will be seeing the radio emission coming from there. And so it is possible that long period radio transients could be some kind of twisted magnetic field structure of neutron star, so that we will still be able to see the radio emission coming from them. So theoretical models suggest that we will still be able to see the radio emission from the neutron star, provided that they are in some kind of very weird like magnetic field structure. So we can explain the high magnetic field these objects have, and why are they able to emit the radio emission even below the deadline based on the magnetic field structure we have. So this tells us that this diagram also reassures that the most likely candidate for these long period radio transients could be some kind of magnetar or white dwarf, or like white dwarf and a neutron star in some kind of interlock system. So this diagram is what that is saying. So now I'll briefly summarize my talk and what lies ahead for the future. So, okay, this diagram is interesting in the sense that, so we don't need to worry about the lower part, the shaded part, because those are all thermal emissions. We are not worried about that. But the upper part, that is what the radio emission is coming from. Overhead radio emission is basically non-thermal emission. And the interesting thing about the upper part is those are FRBs, and those are the pulsars, and the one inside the box are long period radio transients that we have only recently started to discover. But most of those regions are like empty. And it's so just a few years back, we didn't know about these things existed in the universe. So now we have started to know that okay, these things exist in the universe. So this is interesting for like future astronomer, that it is very likely that we will start to discover some objects. There is like a lot of gap, like empty white region. So that is telling okay, it's likely that we will start to discover some objects in those regions. For instance, if we see the FRBs and the pulsar, they have almost like similar range of period, but in terms of the energy budget they have, FRBs are very, very high energetic events. And if we compare the pulsars and the long period radio transients, in terms of the energy budget, they are comparable. But the period of long period radio transients are like much higher. So at some point in the future, we might discover some objects in that region which has comparable energy with the FRBs, but has a very long period. And that would be very interesting, like what kind of objects might we have in that way. So these white spaces, empty region is telling that there are a lot of interesting discoveries awaiting for us in the future. Okay, so these are some of the future projects that have been proposed for new radio telescope. So the SK precursor has already been built, and probably this will soon be complicated. It's like Australia, most of the interferometer will be located in Australia and South Africa. And the cord is the updated version of time, and probably like Green Bank will also have some of these dishes. But this is in the pipeline and will probably soon be completed. And the DSA, that is also a proposed new radio interferometer. Probably this will be located in somewhere in California. And the NGBLA is the updated version of the BLA telescope in New Mexico. So we have a lot of new projects, new instruments being built. So with these new instruments, it's very likely that we start to discover new interesting objects, and probably those white spaces that I showed in the previous diagram will be filled up. And especially for the long period radio transients, so I have broadly classified into like 4 categories, the likely future world. So one is that most of these long period radio transients we have discovered so far were discovered accidentally, but now we know like 6 or 7 candidates, and we know some of their physical characteristics. So based upon that, we can design a radio survey. And when we have a dedicated well-designed radio survey, especially looking for that, so probably we'll start to discover 100 of these objects. By now, we only have like 6 or 7, but this kind of dedicated survey will help us discover like 100 of these, because we already know how they might look like, what are their physical characteristics. So based upon that, we can design a well-planned dedicated survey. So that will help us discover more of these. And another one is that some of these long period radio transients were also observed in the past archival data. So somehow we just missed looking at them. So if we go back and look the data for the past survey that has been carried out from the other telescope at low frequencies, I think there are more that we will detect. So the other avenue of research is just like going back to the past archival data and searching carefully. So I think there are some of them, because some of these long period transients were also observed, seen in the past data. That is other avenue. And next avenue for the research for the future is that we still do not know fully about the currently known long period radio transient. For instance, recently there is one that was discovered with a counterpart in it. There was a counter dwarf star with it. So if we regularly monitor other LPRTs in the future, maybe we'll start to see they also have some other counterpart, or we start to uncover like what are the emission mechanism looking like. So the other project is to regularly monitor the known LPRTs in the future. And the last one is that, okay, we have been studying pulsars for about 6 decades now, but we still do not understand well about the pulsar environment. So pulsar magnetospheric environment is very vaguely understood. And the thing that complicates is that at such a high magnetic field and high density, how the particles behave. So the physics is very complicated. So if we know from theoretical and numerical studies, if we better understand the pulsar magnetospheric environment, then we will be able to better constrain the properties of these long period radio transients, and we'll also be able to identify what kind of sources will be responsible for giving this kind of radio emission from these things. So with all that said, I would like to conclude my talk and open to take questions.
Very good. Any questions internally? Got a few here. Go ahead, Esli.
Do these sources have a tendency to have a particular characteristic of the frequency?
So most of these, there are just very few, but from what I have studied, so most of these were discovered on the low frequency regime of the observation.
Like, what do you mean by low?
Okay, so one of these was discovered using the Meerkat telescope in SK that operates at around 873 megahertz. So one was, and the same source was also observed from the SCAT, and that was operating at around like 1.3 gigahertz.
And what is the bandwidth of the observation?
So, for instance, the time has a bandwidth of 400 megahertz, and one of these has been observed from the time as well.
But you're looking at 400 megahertz, but over what bandwidth of that 400 megahertz does the signal become evident?
The time observes not at a 400 megahertz. Time has a bandwidth of 400 megahertz.
And centered on what frequency?
So I don't exactly remember that number on top of my head, but the thing is that it's not the technology. It's not only the technological like problem, because existing technology are able to look at these objects, and of course, like new telescopes that will have better sensitivity and all these things, we'll probably discover more of these.
Yeah.
But even with the existing technologies, we are still able to find these.
It seemed like from your scans, they're fairly narrow signals. They seem to be, they really jump out from the background noise.
Yeah, and also the sensitivity might be another issue. For instance, the there is one that I didn't put in the slide. So there is one long period radio transient that was observed with meerkat, but the same source, the same LPRT wasn't observed with SCAP because SCAP didn't have enough sensitivity as in par with meerkat. So that's why like since now we know few of these, so if we could like figure out the properties of these and design a better like plant survey, then probably we'll start seeing more of these. But even with the existing technology, we are still able to study these objects.
Very good. Oh,
So for many years, optical astronomers have, collaborations between professional and amateur optical astronomers have helped them explore the time domain beyond what you could do with big aviator telescopes, right? So you can only get a little bit of time with a big aviator telescope. So amateur astronomers, have the opportunity and ability to do long-term monitoring. Could you speculate on what a pro-am collaboration might look like for these sources? Because you got a room full of telescopes who might potentially have the time and resources to do the longer follow-ups that KDET does with the SKA precursors.
Yeah, so I don't have definitive answer of that.
Just speculate,
No.
that's all.
I understand, and I even asked with these questions with Professor Down, so probably most of you know him. And he is the one who discovered FRBs. So I asked him like, so if there is anything amateur astronomers, especially radio astronomers, could help in studying this thing. So his answer was probably like sensitivity issue would be the one. And yeah. So, yeah, I don't have definitive answer for that.
How about online? Any questions online? I did have a question for you. So I'm stepping you back a little bit. Is it a correct understanding that to get this data, especially to find such long periodicity, what's the right term? They're gonna be tracking a spot in space for a very long period of time. So I gotta stare at a spot.
Yeah, that is one of the factors because this has very long period, and if we are observing, for example, the one I showed had a period of 6.45 hours.
It's a long time.
If we were observing just for like 3 minutes, for instance, like some FRBs could be like observed like within that time window. But if we just like observe some source just for 3 minutes, then we would not see that in this.
Right. So I guess my question is, since that's the operational stance, it's almost not surprising we haven't really discovered these things, because we don't just sit there and track one spot for that long period of time. That, I mean, now this is in my world, so maybe we do. But I wouldn't think that we do this often.
Too many spots to keep an eye on.
Time domain astronomy is,
Yeah.
it's on.
And the ones that are like, they're probably ones that, like you said, that are days long.
Yeah.
That's gonna be really hard to find.
Yeah, and
Who's got the time and the money?
Well, but the data should be hidden in some of these things like meerkat that are big phased arrays, right? So the data is gonna be there, you just have to look at it in the right.
Somebody's gonna have to crunch a lot.
Right, if you've got a dish and you're aiming it, then you're screwed, right? But if you're looking at one of these fields full of antennas.
Maybe part of your research is not basic science, trying to find stuff hidden in data that you might have.
yeah, and I would just like to like inform this thing. So actually there was one that was discovered at 2005. We call that CRT something. And that had the like period of around 75 minutes. But after 2005, what happened like for all these years, I really do not know. I also asked with like other professors, but it's not like that was just some like random like people just said that claim that they discovered. It was like published in the paper, like scientific paper. It was discovered in 2005, but for some reason I don't know like why it went missing or why it didn't hear.
Right.
And so there's like one source that was observed in the recent observation, and then they felt like, okay, so how about we go back and see all the past surveys done under like low frequency regime, and they could like track back that source like 30 years before. That has been active for 3 decades. So that's why like one of the avenue for the research is like just going to the relevant past survey and like start to dig out.
Have any of your sources like just turned off? Have there been any that you've discovered and then all of a sudden it just stopped? Or are they
Yes.
still all going?
Yeah, some of these sources, they just observe once and in the follow-up observations, they don't see.
So I want to give a huge thank you to Anoj because we're entering summer. He finished up part of the studies. He's going home. He postponed going home back in Nepal to see his family until leaving Thursday, just so he can come down and talk to us. So he taught me SARA tradition. We have a gift bag for you. We thank you very much. We safe travels and hopefully soon to be Dr. Khadak. Maybe you can come back and visit us.
Yeah, of course, I'd always love to come and talk to you. Yeah.
Be careful, we'll hold you to that.